Hello, in this video I'm going to show how to make a transformer network in Keras using the Keras API in Python to translate between English and Spanish. I'm going to do a walkthrough of the example shown by Francois Chollet in the Deep Learning with Python book version number 2. For a background on transformers, you can look at my previous video whose link is in the description of this video in addition to the other reference that I also have in the description. I also have some videos showing how the transformer work. There's a bunch of videos out there about that. The purpose of this video basically is to show how to implement this network in particular that you're seeing here using the Keras API in Python. Okay, so the example that I'm doing is this one. I'm gonna put a link to this in the description of the video as well. If you, I'm using Colaboratory, Google Colaboratory for doing this. You don't have to install anything. You have to do anything. Just go to the link that I put in the description of this video, and you can copy paste all the commands in here. That's what I'm doing. But there's a caveat. If you paste everything directly, it's not gonna work, because it depends on the previous example, which I also put into the description of the video. So I'm just gonna copy the parts from here that are needed into here, so I don't have to walk back. Okay, so now to start, we're gonna download and using wget and unzip the code, and that's gonna give us it's just gonna be a single file that contains all the translation between English and Spanish. And before I proceed, it's very important that you go to edit notebook settings and put GPU, because otherwise these networks take forever to train, and with GPU it takes hours. I guess it takes days with CPU. Okay, so the first part is getting the statements. So let's take a look at how the data looks first. So this is the folder where it is, and this is the file. It's gonna take a while to load. I'm gonna pause. Okay, after a couple of minutes, we loaded the text, and so you can see that the statements, English in the left and Spanish in the right, are separated by a tab. So they start with short sentences and go all the way to large sentences, and they should not have more than 20 words. Okay, so let's close this. Okay. So first, we read the data, split it by new line, so get the lines, iterate through the lines, and split it by tab, which separates between English and Spanish, and we concatenate the start and end token into a Spanish sentence and create the pairs. So now we have the pairs, and randomly we're gonna choose 3 of them and use the random choice to just take the pair. I want $1, quiero $1. Yeah, so the translations are correct. Now we are gonna shuffle the text pairs. As you can see, they are in order, in ascending order depending on the size, and that's not good for the training. You have to shuffle it so that the distribution is more normalized. And the length is about, we have about 118,000 samples. So we're gonna take 15% for the number of samples, which is gonna be 17,000 or something like that. So basically we subtract about 38,000 out of the 118,000. So we're gonna have like 83,000, and then takes the first 83,000 for training, from 83 to 100 or so. They know 83 plus 17 is like 100. So go from 83 to 100 and get the next 17 for validation. And then from 100 to 118 to the end, then you get 17 for test. So you're gonna get, you can see here, well, I guess you can see it better in here. Training pairs, training pairs are gonna be 83,000, 17 for validation, 17 for test. Okay, so now we're gonna create the data sets. That is like a data stores in MATLAB. Basically it's what we're gonna use to feed the neural networks. but we have to do some pre-processing, and that includes the removal of some undesirable characters. So let's import the TensorFlow API, the string and regular expressions modules, and from string we're gonna get the punctuations, and we're gonna include the Spanish question mark. In Spanish you have to put the reverse question mark at the beginning of the sentence, so we're gonna remove those punctuations. And then we're gonna eliminate from the set to remove the square brackets because we need it for the tokens, I guess. Then we're gonna take those characters, and we're gonna use a regular expression escape to put the backslash to each of them, and we're gonna use this syntax, which is like an F in front of the string followed by curly brackets. So that means that you're gonna evaluate this allow evaluation inside strings, and this curly bracket does the actual evaluation. So you can see that the combination of both makes a string that has an 8. You can see it in here. That's what we're doing here. We're gonna do the curly brackets and surround everything by a square bracket. So we have those characters, and that's what we need to fit to this regular expression replace. Okay, but where does that come from? I went too far. In order to fit the English and Spanish sentences into a network, we have to codify them. We cannot just pass the word as is. So let's say in this case we have a vocabulary size of 15,000. We have 15,000 words. So we're gonna encode with a scalar the values of each sentence or of each word. So for example, each word is going to have a value from 0, 1, 2, 3 until 15,000. So I guess that the text vectorization is going to be created to do that conversion from word to number. And I suppose that the smaller numbers are going to be assigned to the most frequent words, and that's why you need to train these text vectorization objects. So the first one is simple. The first one is for the source, which is English. So you have the vocabulary size, 15,000, and the sequence length. You are not going to have more than 20 words, as mentioned before. For the Spanish, it's the same, but you're going to have one more sequence because of the tokens. You're either going to have the initial token or the final token. So, okay, so we're going to pass a callback to this one. And the callback is going to put, this is for Spanish, it's going to put it in lowercase, and it's going to apply a regular expression with what we did over here by removing all these characters. Replace them with blank. So we're going to put it in lowercase and replace those characters in Spanish. And now with that, we have the text vectorization objects. These are important. We're not going to use it only for training, but also we're going to use it at the end where we're going to do the actual translation between English and Spanish. We have to translate the English sentence using this text vectorization, and we're going to see it later, and how we have to also to convert them back. So the target vectorization is going to give us a dictionary that we can convert the code that the transformer network is going to give us to convert it into a Spanish word and be able to complete the translations. So those are important objects. Okay, now we have to train those text vectorization objects. So we're going to take the pairs, and we're going to create an array of only English words. So for each pair in here, we take the first one, which is the English word, and we're going to do the same here. Take the second one, which is a Spanish word. So we only get Spanish sentences in here and the English sentences in here. So the source vectorization, which is for English, we adapt with English sentences only. Same with Spanish vectorization, we adapt with Spanish sentences only. So we're going to train it, and it's going to take a while. Then after that, we're going to create the data sets, and we're going to have a batch size of 64 for them. And here is where we created. We pass the training pairs, we pass the validation pairs, and to that function. And what that function is going to do? It's going to take the pairs. It's going to use this weird syntax. Whoops, I made it even worse. So it's gonna take it's gonna use C basically to separate the English and the Spanish. It's gonna put it in a couple of lists and then create a data set with that. For some reason, the pairs could not be passed directly to here, but anyway, you create the data set with the English and Spanish pairs with the batch size specified of 64, and then we're gonna create a map data set that is gonna apply a callback to those pairs, and we're gonna parallelize it. Okay, what is a callback? Is this one over here, and the input is what we have in the data set, which is the English and Spanish. Again, we already have the vectorization, so we're gonna use the source and target vectorization to translate the sentences into codified sentences. And notice that the target's vectorization is gonna apply this customization. So this is the place. This is the place where the Spanish sentence is turned to lowercase and the punctuations are removed. These punctuations that we have in here. That this is where it happens. So we have the codified English and Spanish sentences, and now we're going to create the input. The input, notice that it's a structure, and this is kind of counterintuitive because we understand that the input for this network is going to be the English sentence and the output is going to be the Spanish sentence, but the input is both the English and the Spanish sentences. And it is like when you're translating from let's say from English to Spanish, you take into consideration the English sentence that you want to translate, but also the words in Spanish that you already mentioned to generate the next word. So the input for producing the next Spanish word is going to be both the English and the Spanish sentence. That's why you have a structure here with a field of English and Spanish. And the Spanish for the input doesn't include the final token. But the Spanish output does include the final token, but does not include the input, the initial token. That's why it starts in 1 rather than 0. Okay, so why a structure? A structure is important because these names in the fields of the structure is what the network is going to use to pair them up with the corresponding input layer in the network. We're going to see that in a moment. Okay, so after having this, we're going to have the data set and we're going to shuffle it because we want to shuffle it. The order was not good for the network, as mentioned before. We're going to prefetch it and do some things to make it more efficient. And now we have the data set for training and validation. Okay, so let's take a look. Let's run it. And let's take a look let's convert the data set into an iterator so that we can convert it into a list. And then we get element number 50 and just print it. But also let's gonna print out the shapes. Just let's take one element, and basically we take the inputs and the targets, and the inputs you can see that is a structure. We have the English field, the Spanish field. We take the shape of each one of them and let's print it out. And you can see that the shape is 64 because we have a batch of 64 sentences. And each sentence cannot be longer than 20. And you can see that in here. They are codified. So each code of this that you can see here, this is a word. Those are words. Actually, this is I forgot the code of this word, but anyway. Okay, so this is the English field. This is the input. This is the input. And this is the output. In Spanish. Notice that this is the code for the initial token, and these 20 correspond to the same as the output. But these are the same words, notice, because it's the same sentence. No, but this one doesn't, the output doesn't have the initial token, which is this one, as mentioned before in here, because of this. Okay. So these are your codified data set. And now we're gonna import the Keras and API, the layers API. Now we're gonna, before creating the transformer network, we're gonna create a classical recurrent neural network to compare how good the transformer compares to it. Okay, so this is gonna be very simple. So we're gonna have an input for the English, and that English goes into an embedding layer. The embedding layer it's going to convert the code that we see in here, which is a scalar, into a vector that represents the semantic. So in this case, the embedding is going to have 256 elements. So it's going to have each of these 256 elements has a semantic value. It could be a quantity, gender, location, etc. Any semantic depending on the text for which you are training it. The vocabulary size is going to be 15,000, and we're going to have a mask. The mask concept is important both for the GRU and also for the transformer, because the way that the Spanish statement is generated is word by word, and as mentioned before, one of the two inputs are the English sentence and the Spanish words that you have generated so far. But in the training, you have the full Spanish sentence, and you don't want to fit the full Spanish sentence into the network for training. So you want to mask it. So the word that you're focusing to generate, you want to put in 0 the other words that go after it, and that's the mask. So we're going to say that we have a mask for the embedding, and so the output goes into the bidirectional layer, the GRU. This is a network that is based on states. The recurrent neural network has a state to have the context, and that's maybe an indirect way to having an attention. They have compared it like that, I think. But the transformer network doesn't have a state. They just use matrix multiplication that creates the attention mechanism between the words in the sentences within English, within Spanish, and between the two. That's what the transformer is doing, but it doesn't need a state. But this one has a state. Okay, so the input, this is the GRU, this is the encoder part, and then you have the decoder. So it could be seen something like this. So this is a sequence-to-sequence problem from MATLAB. It's not exactly the same problem, but it shows more or less what the problem is in the GRU, the network. So you have the input sentence, which is English. You encode it, and at the end you have like a context, and that's going to be your initial value for the next decoder. So the decoder is going to take the Spanish, and it's going to produce the Spanish word or something like that. It's not exactly the same, but that's more or less the idea for this GRU. Okay, so for the second input is the Spanish. And you can see in here, you have the name. This name is important. As mentioned before, this is going to be a structure, and those English and Spanish names are going to be matched into here, so they can take the proper input. Okay, so again, we have an embedding also for the Spanish, and we also going to mask it, and then the output is going to fit into a GRU. But notice, the GRU, we create the layer first. We put the latent dimensions, which is the same here. That's kind of the state size, I understand. We're going to return sequence, and then we call it as a function, and the input is going to be a couple of inputs. One input is the Spanish that is encoded in here, and the English that was encoded in here, and the output is going to be fed into a dropout for regularization, and then you're going to have a dense layer, and the output is going to be the word size, vocabulary size. And why is that? Because we have 15,000 words, so for each 50,000 we're going to get a probability. So each word in the vocabulary is going to get a probability, and the higher probability is going to be the word that the network selected. And that's the same output in the transformer network, as we're going to see in a moment. Okay, so we have the dense layer, and that's going to be the output, the fully connected layer, the dense layer, and the inputs are going to be the source, which is the English, and the Spanish. So we have the recurrent neural network model. We have the summary here. We just run it, and then just run it in here. Okay, this is a summary. So we have the embeddings, 256 semantic vector, and then we have the bidirectional GRUs that has a size of 1024. The dropout, which maintains the same dimensionality, and at the end we have the 15,000, which is for each word, the probability for each word. So now that we have the network, we compile it with RMS prop, categorical cross entropy, the metric is accuracy, and we then use the fit method in the model to train it. We pass the trained data set that we created, which with the encoded words, and we pass the validation data set that we created, and we're going to train it for 15 epochs. And I'm not going to run this again because it takes almost an hour. And after 15 epochs, the accuracy is going to be 64%. Not bad, not bad. Let's see how we do with transformers, with the transformer. But before, I'm going to do the actual translation, because now the model is trained. So before, as mentioned before, we have a vectorization, a text vectorization object, which converts from a word into a code. And that's important for the network. But the thing is that the network is going to return a code for the word in Spanish. So right now what I'm going to do is I'm going to use the model that is trained to translate the English sentence into a Spanish sentence. And the same thing that I'm going to do here for the RNN, I'm going to do it for the transformer. So the same explanation applies for both. Okay, so again, the text encoder goes, the text vectorization object, this one here, goes from a word to a code. But now the network is going to return us a code. So we have to go from that code to that word, to a Spanish word. So we get the vocabulary for the target, which is a Spanish vocabulary. And then we get the length of it. We create a range. So we have a dictionary that goes from an index, which is the code, to the word in Spanish. That's all we're doing here, a lookup table for that. And the sequence length, of course, each sentence does not have more than 20 words. So we take the test pairs. The first one, which is the English ones. Okay, so we have 17,000 of those, and randomly we pick one of them. So my boss never invited me to her house. Okay, so let's go through a series of steps. The goal here is to do this code. This code here is the one that is going to take a sentence in English and it's going to translate it into Spanish. So we're going to go step by step because it's a little bit confusing. Okay, so the first step is to take the input sentence and tokenize it, convert it. So in this case, you can see that this is the sentence. And now, after using the source vectorization, which is the text vectorization that we created earlier, we have the code in here. We have, you can count the words, it's about 10 or something like that, and it should be the same in here. So you can see the codes in here. So yeah, after that, we now gonna create the sentence in Spanish that begins with the start token. And then that token, we're gonna vectorize it. This is a text vectorization for Spanish, and then we pass the word, the sentence, which is the initial one, and we get the coded sentence, and you can see it in here. And it's no surprise, everything is in 0 because we only have one word, which is a start token, is number 2. And then we call the train RNN model, the predict method, pass the input English sentence, the input Spanish that we have so far, and we get a prediction. The prediction, notice that we're focusing on one word at a time. This is the word dimension. This is the batch dimension. We're gonna put it on 0 because we are focusing on the first statement of the batch. And so we get all the third dimension is the word index, which goes from 0 to 15,000. So we're gonna get all of them. And if we get the shape, you're gonna see that is 15,000 here. And if you print this, you're gonna get a bunch of probabilities for each word. And you can see, then we use argmax with those, so we get the index of the word with the highest probability using argmax. So that is gonna give us the code for the word that the model predicted. And after that, we use the Spanish dictionary, which we created up here, which goes from code to word. And then we get the Spanish word, and we can print it. You can see that the code is 22, and the word is me, which is my in English. Okay, so we concatenate that to the sentence. So the sentence now is start, which is start token, and me. And then we get the concatenated sentence, and we use the text vectorization to encode it again. So we encode it and pass it again to a predict method of the model along with the English sentence encoded, and we get the next word. We again use the argmax, we get the code for it. So the next code is 80, and we use the dictionary. 80, that means nunca, which is never. So we concatenate it and we have the sentence here. So far we have start mi nunca, and that's my never. And what was the sentence? It was my boss never, my never. So it's getting something. Okay, now this is the full code. So what we're gonna do is gonna take pairs. The first pair, which is the English one, only English sentences in here, and we're gonna take 20 of them random by random, and then we take the English sentence, print the English sentence, and run the decode. And the decode is gonna translate the English to Spanish using this. So yeah, again, it's gonna take the English sentence, it's gonna codify it only once, start assembling the Spanish sentence with a start token, and then convert it as we saw before, codify it, pass it to the RNN model with the predict method, codified Spanish, codified English. We get the vector of the word, we get the argmax to get the code for the output word of the network. And then notice here that we're focusing on that particular word in here. We iterating through here, this is the particular word, and notice that when we did here this, the first was 0 and the second one was 1. So that's the word that we're focusing on when we use the argmax to get the code for the word. Then we use the Spanish dictionary to get the word, and we just concatenate it to the decoded sentence, and we continue. If the token is end, we break. But you can see that the accumulated sentence is decoded, codified again, and passed again to the model to predict the next word. And then we just return the decoded sentence, and let's take a look of how, again, the RNN had 64% accuracy. So let's see how it does. I can't believe that you actually got into Harvard. No puedo creer que realmente it has problems with unknown words. So let's pick up a translation that doesn't have those. Let's pick up this one, a very small one. Well done, guys. Nosotros lo hizo. That means we did it. Well, not that far, but it doesn't make sense, this translation. Let's take the next one. There was no place to buy food. No había tiempo ni para comprar comida. What he's saying is there's no time to buy food. He was confused on that one, so that's not a good one. Let's see if there's a good one. Tom heard Mary talking to John. Tom la gente habla a John. It says Tom the people talking to John. It doesn't make sense. There should be one. There should be a good one in here. Let me see. Tom bought some bread. Tom compró algo de beber. This says Tom bought something to drink. This is well, it's doing terrible. I think the transformer is gonna do better. The transformer accuracy is not gonna be that far, but it's gonna do a little better. This translation thing is not easy. Okay, so now let's go to the transformer. Okay, so for the transformer, we're gonna implement, as mentioned at the beginning of the video, this network. The first part is the encoder, which is this one. We're going to assemble this with the encoder. Then we're going to go with the decoder. And finally, we're going to take the positional encoding. Notice that each layer in the transformer has a multi-head attention. That's the new layer. It's a Keras layer, a layer available in Keras. Okay, and it's basically a matrix multiplication. It has the concept of key, query, key, and value. And it's basically apply a matrix multiplication and has a number of heads, which is kind of a repeated layers in here. And basically it's a multiplication of the query, key, transpose, and multiply by value. And by doing that multiplication with the 3 inputs, you get the attention. And notice that the inputs for the multi-headed is just the inputs. In this case, this is the English. So, and this is Spanish. But this one, it combines the Spanish and the English. So there's a like a self-attention, like correlating words in the English sentence, and this is correlating words in the Spanish sentence, and then this is correlating words between the Spanish and English to predict the next word. Okay, so let's take a look. Yeah, so the init method in the encoder is just basically taking the arguments and creating the layers, in this case the multi-headed attention, which is a Keras layer, and embedding them is the size of the embedding semantic vector, the number of heads, which the author is going to use 8 in this case. Then we have a sequential, which is the dense layer. In MATLAB they call it fully connected layer, which has a ReLU for regularization and a couple of normalizations. So you can see that we have 2 normalizations, 1, 2. We have a feed forward 1 and a multi-headed that corresponds. Okay, now the call is gonna turn the input into the output. It's gonna do the actual computation. As mentioned before, we have a mask. I understand that the mask is needed for the Spanish side, but I don't know why it's putting it into the encoder side. But anyway, so that mask, if one is provided, is passed to the attention. In this case, the start is the inputs. The input of which is gonna be the English is gonna go to the first attention, and the attention, you notice here the residual connection. So the input is passed and added, and then goes through a layer normalization so that the input information is not lost, and added to the output of the attention. So that residual connection, you also see it in here. And then that is feeding a dense layer that goes through normalization, but also there's a residual connection that creates the output of the previous normalization and the output of the dense layer, and you can see that residual in here. So it's identical. Okay, so now we have the encoder. Now let's go to the decoder. The decoder, again, the init is going to create the layers and take the fields. So it's going to have 2 multi-headed attentions. Again, they're going to have the same number of heads of 8. And then the sequential, again, is 1 sequential with ReLU in between, and a 3 normalization layers. Okay, let's do the count. So we have a couple of multi-headed, 3 normalization, and 1 fully connected layer, then dense layer. Okay, so it's the same. So this is to get the configuration. You can ignore that for now. This is to create the mask. As mentioned, this is more important. As you can see, it's more elaborated in the Spanish side rather than the English side, because the Spanish is the one that we want to predict, and that's the one that you want to mask. And the mask mechanism is as described. It can become confusing, but the concept is simple. You want to ignore the words that go after the current word that you're predicting. Okay, so the heart of this decoder is in here. You take the input. Notice that you take the input, which is going to be Spanish, and the encoder output, which is the English encoded, which is this. You can see this input here and this input over here. Those are your 2 inputs for the decoder. First, you're going to create the first attention that goes to all the inputs. You see the 3 inputs. That's the Spanish. That is right here, the 3 Spanish. And then you have a residual connection with the normalization again, and you have the output of the first attention is passed to the first normalization with the residual connection and the output of the attention, and then you go to another attention, and then the output of the first attention goes to the input of the second attention, and the other 2 inputs are not the same, are just the encoded output. So you can see it the same in here. You have 2 inputs, encoded outputs, and the input of the first attention, and then the residual connection with another normalization, and then the output goes to a normalization, then with the residual connection of the first attention, and then the output goes to a dense layer with another residual connection, and that's basically your decoder. Finally, so we have the encoder and the decoder of the transformer. So we have this one and this one. Now we have to create a class for this positional encoding, and as mentioned before, the sentence is going to have a vector for each word. There's going to be a vector of semantics. To that vector of semantics, which we get through this input embedding in here, we're going to add the position of the word. So that's what this class is going to do. So let's go to the positional encoding. I think I run this. I'm going to run this again. And for the positional encoding, again, we're gonna create the embedding layers. We're gonna have an embedding for semantics and an embedding for position. And then we're gonna, this is the heart of it, the inputs. We're gonna take the last dimension, which is this dimension of the word, which understand should be 20. And then you create a range, so you're gonna create a vector of values from 0 to 20. And that position is gonna be fed to the position embedding. The input is passed to the embedding, and that semantic embedding, the one that I'm pointing to, is the same that we saw in the RNN. It's basically just for semantics. So we have the semantics embedding and the position embedding, both of them are added. And that's how it is indicated in here for both. So it's gonna happen for both the English and Spanish. So let's take a look at the network now. Let's just run this. And it's very similar to, a little bit similar to the RNN. You have an encoder phase, you have a decoder phase. For the encoder, we have the input, which again is gonna point to the English input. And then that input goes into the positional embedding. The RNN has a regular embedding for semantics. This has a positional embedding, which has semantic and position embedding. So this is your encode, this is embedding. And that is passed to the encoder transformer. The encoder is gonna have the number of heads, which is 8. The dense theme, this is for the fully connected layers, for the dense layers in here, the blue ones. And yeah, so basically you're gonna get the encoded English in here. Then it goes to Spanish. The Spanish is gonna be passed through the same positional embedding. You're gonna get the output, and the output, notice that the transformer decoder is gonna get two inputs as mentioned before. It's gonna take the encoded English and the encoded Spanish, and you get the output. The output goes to a dropout for regularization, and this final layer, the dense layer with a softmax with the vocabulary size, is going to be the same output that we had in the RNN. It's going to be from a vector of 15,000 elements, in which each element corresponds to the probability that a particular word is the word that is being predicted. Okay, so with that we got the output, we got the encoder inputs, which is the English input, the Spanish input, and the output, which is the word predicted. We got the transformer, and then we just get the summary, and the summary is very simple compared to a CNN. And the inputs, the position embedding has the 256 dimensionality, and the transformer respect the same dimensionality and the dropout as well. And finally, the final dimension is the number of words that we're gonna predict. Okay, now again, we compile and train this in the same way that we train and compile the RNN. We call the compile method with RMSprop, categorical cross entropy, and I don't find this fair. It took me a couple of hours to run this, but the RNN, for some reason, Francois run it for 15 epochs, and this was run for 30. I think a more fair comparison would be running the other one for 30. I didn't have the time to do that. Okay, so it passes the trained dataset and the validation dataset, and in 15 iterations, you can see that it reaches to 65 accuracy, which is not that far from the other. So the maximum accuracy that it gets is 66. And yeah, so at the end, again, we're gonna do the same thing that we did with the recurrent neural network. We're gonna have the code sequence which behaves exactly the same. We're gonna take the test pairs. We're gonna take the random English sentence. We're gonna print the English sentence, and then we're gonna use this method to decode the English sentence into a Spanish sentence and print it out. So again, it's gonna take the vectorization, which is the same with that one that we use for the RNN. So we got the encoded sequence. We start to assemble the decoded sequence. We pass the codified English and Spanish. We get the prediction from the transformer, and then we get the Rmax and for the focus word, and that's gonna give us the code. We have a dictionary, which is the same, taken from the same place, and with the code of the word, we get the words concatenated, and we break. It's exactly the same. So now the output it's gonna be this. So we have a 66% accuracy. Let's take a look at this one. We're not your enemies. No somos tu muerto. It's saying we are not your dead. Again, that's garbage. Okay. We will be at home today. Hoy vamos a estar en casa. Actually, this is a perfect translation. Let's take another one. What is this thing for? ¿Para qué es esto? Another good translation. Okay. My father likes pizza very much. A mi padre le gusta la pizza está muy mucho. He's saying, my father likes the pizza, but it's too much pizza or something like that. But it's not that far. I think the validation accuracy looks about the same, but looking at the sample looks much better. Except this one right here. Tom shot Mary in the knee. The translation is Tom le dio una a Mary. Tom gave one to Mary and then starts saying la 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 la. I don't know where that came from. Okay, so that's it for the video. Thank you.